Our final public lecture is by Anna Archibald, and it's on Does Extreme Gravity Affect How Objects Fall? Thank you.
Thank you. I noticed the level of the previous public talks has been rather advanced. I'm impressed with the level of public education in Italy. But we're all at the end of a long week, so I'm trying to make this talk fairly accessible. And this is a talk about a test of Einstein's theory of gravity, of general relativity, that's been made possible by the discovery of a remarkable stellar triple system. And I should say that if you'd like more information, there's the paper just appeared in print yesterday, and if you're interested, I'd encourage you to go read it. If you'd like less information, or you'd like this to be friendlier, we created a short YouTube video explaining it. So depending on where in the spectrum you fall, I recommend either or both of those. So this test of relativity is a test of really, excuse me, a test of kind of the most fundamental aspect of gravity, which is how do objects fall? And the ancients had a theory. Aristotle had this theory of how gravity worked. Objects tended to move towards their logical place. And in his theory, heavier objects fell faster. And this was more or less accepted for hundreds of years. There was some doubt, and Galileo really questioned it. And he questioned it on logical grounds. He imagined tying two objects together. If the rope broke, did they suddenly start falling slower because they were separate objects? So he argued with it on logical grounds. The story is that he dropped two cannonballs off the Leaning Tower of Pisa. It's not clear that that actually happened. But the early Dutch scientist, Simon Steven, describes actually doing this, going to the tower of the Nieuwe Kerk in Delft and dropping cannonballs off and concluding, he says, that Aristotle had been wrong, that indeed massive objects and light objects fall at the same speed. And there was a lovely demonstration when Apollo 15 was on the moon. Dave Scott, one of the astronauts, you can actually watch it on YouTube, it's a video, and he thanks Galileo and all the theory that followed from him for making it possible to get there in the first place. And as a thank you, he demonstrates that a hammer and a falcon feather fall at exactly the same rate when you're in a vacuum on the moon. So Galileo had sort of argued that that objects fell the same way. And so when Newton built his theory, this was the first mathematical theory of gravity. I mean, he had to build the mathematics to do it. He built in the idea that all objects should fall the same way. And before he built that into his theory, he did some experiments. He actually built pendulums of different materials and checked that they swung at the same rate to confirm that it didn't matter what an object was made of, whether it was, the rate at which an object fell did not matter what it was made of. And specifically, in mathematical terms, he said, well, force is proportional, acceleration is proportional to force, and the coefficient, the mass, the inertial mass, is the resistance to acceleration of a body. And when he wrote down his theory for gravity, is the force due to gravity, it's gmm over r squared. Well, those m's are the susceptibility of a body, or how strongly a body couples to gravity. And call it the gravitational mass. And Newton concluded from his pendulum experiments and from other people's work that inertial and gravitational mass were the same. They never differed for any object. And so he built that into his theory. And the conclusion of which is that the acceleration is independent of the mass of your object and composition. So Newton's theory had kind of built it in, and Newton's theory did a great job for a long time. And when Einstein set out to build his theory, he actually thought of this as a central point. In fact, his argument was, I'm not quoting here, if everything falls exactly the same way, if all that matters is where it is, it has no dependence on composition or size, maybe gravity is not really a force in the sense that the electric force is. Maybe it's just the geometry of space-time. Maybe objects that are falling are just following the straightest path they can through curved space-time. And so Einstein took this idea that gravity is really just geometry and built his theory of gravity, general relativity, out of it. But this only works if all objects fall the same way. If objects fall differently, then gravity isn't just geometry. So this is a cornerstone of relativity. And so when we're looking for alternatives to GR or trying to test GR, we break it up into pieces, equivalence principles. And there's a great paper titled Non-Equivalence of Equivalence Principles that lays out the complete complicated logical structure of all the different formulations of the equivalence principle. I won't go into that. But the first thing, the easiest one, is the one that Newton tested, the weak equivalence principle. And that just says, that the following all fall identically. Proton rest mass, nuclear binding energy, electrical magnetic field energy, all of this stuff. Or put another way, gravitational mass and inertial mass are equal regardless of composition. And this is something you can test in a laboratory. You can build a delicate torsion balance with a copper test mass and a uranium test mass and see if they respond the same way to the gravitational pull of a nearby hill. This has been tested at 10 to the minus 13 level in laboratory experiments. The microscope satellite has now tested this to the 10 to the minus 14 level, and they're hoping for 10 to the minus 15. This is pretty well established. And this allows you to use what's called a metric theory of gravity. Gravity is not only geometry, but at least geometry can be used to describe gravity in a kind of familiar way. So the weak equivalence principle is well established, and I'm not going to kind of challenge it here. But the strong equivalence principle is what Einstein needed to build his theory. And this goes a little bit further. This is Einstein's classic laboratory in an elevator experiment. If you build your laboratory in an elevator, you're allowed to do chemical experiments, nuclear experiments, mechanics experiments, even gravitational experiments inside the elevator, and you can't tell with any of those tools whether you are sitting still in the Earth's gravitational field or whether you are accelerating upward in free space. Now, I'm not going to talk about all of that. It has a bunch of requirements, but specifically what this means is that gravitational mass equals inertial mass. And that's the weak equivalence principle. But here, it's not just composition. It includes objects with strong gravity. So for objects with substantial gravitational binding energy, inertial and gravitational mass still are equal. Or put another way, gravitational binding energy falls the same way as all those other kinds of mass energy. Or put another way, all objects, no matter how strong their gravity, fall the same way. Now, why am I making a big deal of this? Why is gravity special here? Well, in post-Newtonian theories, in all post-Newtonian theories, and actually as measured in our solar system, in order to make the periastron advance of Mercury work out, we know that gravity has a nonlinear superposition. That if you take an object with substantial gravitational binding energy, there is a nonlinear interaction between that gravitational binding energy and an external gravitational pull. And it would be an astonishing coincidence if the combination, that nonlinear combination of those two kinds of gravity, were to work out to the massive object falling the same way as a non-massive object. And in fact, it's almost only Einstein's general relativity where that works. In almost every other theory, that doesn't happen. The motion of a really massive object is different in almost every other theory. That almost has a big asterisk on it, but this is a foundational idea behind general relativity, and this is a really good aspect of it to test because it's a way general relativity differs from almost all its competitors. So how would you go about actually testing it? Well, let me give an example of a competitor. In the, I think, 1950s, the Brans-Dicke theory was put together, and its idea was to satisfy Mach's principle, which is an idea that sort of inertia and gravity shouldn't just be absolute concepts. They should come in the spirit of relativity from the matter around you. And to some extent, general relativity itself satisfies this with lens theory and precession, but to some extent it doesn't. There's still a kind of absolute space of a sort. Inertial frames are kind of absolute in relativity. And so Brans and Dicke decided to try and extend Mach's principle. And what they ended up doing was adding an extra scalar field, phi, that pervades space, just one number at every point in space. And the effect of that is, its effect on physics is actually what they call minimal coupling. So if you do any normal experiment, normal physics proceeds with a slightly modified version of the normal space-time metric. It's just scaled by a function that involves this scalar field phi. And this scaled version of the metric means that chemistry, nuclear physics, all that stuff looks the same locally. The difference is that if you do a Cavendish experiment, if you measure big G, that's going to come out different. So Brans-Dicke satisfies the weak equivalence principle, but it fails the strong equivalence principle. And there's a parameter alpha naught that describes how much difference phi makes to your local physics. And so, unfortunately, this theory is hard to disprove because you can turn alpha naught as small as you like, and then it has this sort of negligibly detectable effect. Nevertheless, philosophically, there's a reason to consider this extra scalar field, and because phi is generated in matter, if you have a massive object like a pulsar, it will have a scalar field in its vicinity, and therefore it will fall differently. So this is a theory that violates the SEP and would produce massive objects that fall differently from ordinary objects. And it's sort of philosophically motivated. There are other more modern ones that are more complicated, but this is an example of an alternative theory that would potentially be flunked by a test of the SEP. But of course the problem is, how do you test the SEP? You have to drop objects that have substantial gravitational binding energy, and you can't really make those in your laboratory, unless you've got a very big laboratory. So there have been a couple of approaches to doing this. The first is lunar laser ranging. When Dave Scott, among others, when the Apollo astronauts went to the moon, they left retroreflectors. And so now you can bounce lasers off the moon and get distance measurements. And so there are 35 years of centimeter level distance measurements to the moon. And this means you can ask, do the Earth and the moon fall differently in the sun's gravity? So this is a very sensitive test. This is the best test up until yesterday. And you know, it's testing precisely what we want to know. Do they fall with the same acceleration? The problem with this test, that what limits its sensitivity, is that the Earth's gravitational binding energy is something like a billionth of its mass. The Earth's gravity is not that strong by astronomical standards. So can we do better? Well, earlier this year, Weiwei Zhu published a nice paper where they took a pulsar and a white dwarf binary that can be measured very precisely and that are falling in the galaxy's gravity. And here, the pulsar's gravitational binding energy is something like 10% of its mass. And so here you've got a huge difference in gravitational binding energy. And so if ever there was going to show up a difference, it should show up here. The problem is that the accelerations of the two bodies are both really, really small, because the galaxy's potential well is not very steep. The galaxy doesn't produce much acceleration. So this one is limited by the limited acceleration these objects produce. So it's a good test, and it tests the strong field regime, but it's limited. But this paper happened because we now have a system where the test body's gravity is strong. We've got a pulsar, but you actually have a substantial external acceleration as well. So you get the best of both of these tests. And this is possible because we found a pulsar in a stellar triple system. And so its name, I apologize, is PSRJ 0337 plus 1715. They get telephone numbers. But it was found as part of the 2007 GBT drift scan survey with a broken telescope. But what the system is a pulsar, millisecond pulsar, in a 1.6-day orbit with an inner white dwarf companion. And that inner binary is in a 327-day orbit with an outer white dwarf companion. So this is a hierarchical triple. It's stable. It's going to be like that for the long term. But this allows us to do the same sort of test as the Earth-Moon-Sun test, but with a pulsar as our test body. And the fact that it's a pulsar is great. And I say this not just because I think pulsars are awesome, but because pulsar timing is an incredibly powerful tool. The fact is that if I were to boot up Arecibo and point it at this system right now and use a predicted ephemeris to average for 20 minutes to get an average pulse from the pulsar, it would look almost exactly like the right panel. The only difference would be there'd be a bit of noise, and it would be either a little bit early or a little bit late. And as long as it's the same shape, you can use cross-correlation to very precisely measure how early or how late. In fact, we can measure how early or how late it is to the nearest microsecond. And so this is a precision measurement we can carry out on an astrophysical object. This is great. But the other thing that makes pulsar timing so powerful is that we can account for, the pulsar is such a stable rotator that we can account for every single pulse since we started observing. So I can say, for example, that pulse number 56,528,015,489 arrived on 2017 May 14th, 1951 17.9937500 UTC. And so, for example, if I wanted to measure the pulsar spin period, I would take that 6-year period that we know to the microsecond, I would divide it by 56 billion, and I would get the spin period to, in fact, we know it to 12 decimal places. Now, nobody cares about the 12th decimal place of a pulsar period. There's no physics there. But when you have a pulsar that's not isolated, that's moving around, the pulses can arrive early or late because the pulsar has moved. If the pulsar is in front of the plane of the sky, the pulses arrive early. If the pulsar is behind the plane of the sky, the pulses arrive late. So in fact, every one of these microsecond level measurements is a measurement of the line of sight distance to the pulsar to the nearest 300 meters. And so this precision measurement of the orbit is fantastic. We have a very detailed picture of the orbit. I'm sure you can't read all the numbers on here, they're not important, but the point is we have measurements of the orbit that just from the pulsar alone, we're able to reconstruct the inclination angle, the mass of the pulsar, all of this structure of the orbit based on purely classical three-body interactions. So we have these great measurements of the system's orbit. And we can hope that these great measurements of the system's orbit will translate into answering the question, is the pulsar falling differently from the white dwarf? So, I should say, before I go too much further, that there's some interesting astrophysics here, that it's very difficult to form a millisecond pulsar in a triple system because triples are kind of delicate. A binary, you actually have to remove mass or introduce energy to separate it. A triple, you can always steal energy from the inner system, put it into the outer object, and eject it. And this system has to have survived a supernova plus one or more phases of mass transfer. There's actually 2 dueling papers on whether it's 2 or 3 phases of mass transfer in a common envelope. So there's some interesting astrophysics in the formation of the system. It's not clear how it came to exist. It's clearly rare, but we don't know how it got there. There's also some interesting astrophysics about the white dwarf, which we actually know more about than most people studying white dwarfs ever will. So there's some very interesting astrophysics in this system, which I am going to proceed to completely ignore, because I'm more interested in the test of gravity that we can do. Excuse me. So to carry out this test of gravity, we have 6 years of observations, 800 observations, 1,200 hours on sky, with Arecibo, Greenbank, and Westerbork, 3 of the best telescopes in the world. So we have a fantastic data set with which to study this pulsar. We used this technique of pulsar timing. So we compared the radio signal, this sort of radio pulse that we observe, to a standard template to see sort of whether it was early or late compared to a simple model. Our data is all from 20 centimeters, from 1400 megahertz or so. There's a complicated asterisk there, but we're using essentially 1400 megahertz radio observations entirely to do this project. And we're able to extract 1 pulse arrival time every 20 minutes by 20 megahertz. So we get bunches of about 20 pulse arrival times every 20 minutes. So we have 27,000 microsecond level measurements of the pulsar's line of sight distance. So this is a fantastic data set we can compare the pulsar's motion to. But of course, we need a model for the pulsar's motion. And as some of you probably know, it's been proven that there is no closed form solution to the 3-body problem. And more relevantly, there's no good enough sort of Keplerian series expansion approximation. There's no formula we can use to describe this motion easily. Fortunately for me, you can do this the dumb way. You just write down F equals ma. You just write down F equals gmm over r squared. That gives you a bunch of differential equations for acceleration in terms of positions. You feed them to your computer and tell it integrate these differential equations, and you get a simulated orbit. You have to do this many times for different parameters, but you can simulate orbits just fine. And you can compare the pulse arrival times you infer from those orbits to the pulse arrival times that you actually measure. So this is a workable scheme for modeling the orbit. Now I will say, that's Newton's laws. In Newton's laws, gravitational mass and inertial mass are the same idea. But it's not actually a problem to put the distinction back in here. You just put inertial mass in F equals ma, you put gravitational mass in gmm over r squared, and you're good. I should also say that the inner system is not very relativistic. It's not a very close system in which all kinds of relativistic effects happen, but we are so sensitive to the orbit that in principle we could detect periastron advance of the inner binary, even though it's nearly circular. So we need actually a model that handles the relativistic effects. And we have one. It's complicated, but it is also flexible enough to handle not necessarily GR physics, and it's flexible enough to handle, in particular, strong fields inside the bodies that might give rise to a different gravitational and inertial mass for the pulsar. So we have a sufficiently relativistic model to do this same direct integration of the equations of motion and get orbits. So in principle, it's easy from here. We have a timing model which has a bunch of orbital parameters in it, and also our SEP violation parameter, delta. So in principle, you just put this in your timing model, you fit the timing model to your pulse arrival times, and you determine the best fit values and uncertainties. And the value of delta and its uncertainty tell you whether you agree with Einstein, and if you do agree with Einstein, it tells you how well you can constrain deviations. The problem with this is that we're sort of too sensitive, that this only works if your error model correctly handles all the systematics that are present in your data. And if I just do this, the level at which we can detect deviations in the orbit is 7 nanoseconds. And 7 nanoseconds is about this far. And so there are a lot of systematic effects that might introduce a 7 nanosecond delay or shift our apparent orbital position by 7 nanoseconds. So we need to do something about the systematics. And I think for a public lecture, I won't go into any details, but we made a list of all the ones we could think of. We fixed the ones we could. We bounded the ones we couldn't. And we have some unknown ones that so we developed a procedure to estimate to what level the systematics could be affecting our data. And once we've taken that into account, we find a result that's consistent with general relativity, and we develop a 2 sigma upper limit. And so the physical statement that we can make is that if you take a 1.4 solar mass neutron star and a white dwarf, and you drop them in the gravitational pull of a third body, they will accelerate with the same acceleration accurate to 2.6 parts in a million. So this is physically the statement that we can make as the result of our calculation. And if you have a pet theory of gravity, let's say Einstein ether, in which the pulsar acquires some anomalous acceleration, let's say by rotating relative to the ether, it gets some acceleration in the direction of rotation perhaps, you should calculate how much extra acceleration that is, put it in here, and see if it comes out to more than 2.6 parts in a million. If it does, your theory's in trouble. So that's great, but 2.6 parts in a million is just kind of a small number. It's not easy to understand what it means without some context. So let's try and compare this result to some existing tests. So the easiest test to compare it to, the most similar physical situation, is this result of Weiwei's use, where he's looking at, again, a white dwarf and a neutron star, about the same mass, falling, in his case, in the galactic potential. And he's able to compute an upper limit on the acceleration for that system at the 10 to the minus 3 level. And so we improve on his result by a factor of almost 1,000, which is great. But let me emphasize, this is not because we are more clever than Weiwei. He's a smart guy. This is because we have a system where the third body provides a very substantial acceleration, and he was stuck with just the galaxy's acceleration. So we have a much better system to work with than he did. But Weiwei's result is unfortunately not really the best test of the strong equivalence principle to date, or till yesterday. The best test came from lunar laser ranging. And that's a system where the Earth is a very different body from the neutron star. So we're going to need to do some more work to compare that to our result. So to first order, there's just a theory parameter, the Nordtvedt parameter. What that is how differently gravitational binding energy falls from the rest of an object. And so to calculate how much an object violates the SEP, you take its fractional gravitational binding energy, you multiply it by the Nordtvedt parameter, and you get an amount of SEP violation. So for the Earth-Moon-Sun system, their acceleration limit is at the 10 to the minus 13 level, which is fantastic, much better than ours. Did I mention the 35 years of centimeter level measurements? They've got a great acceleration limit. But then they have to divide it by the 10 to the minus 9 level binding energy of the Earth. And they're left with a 10 to the minus 4 level constraint on this theory parameter. Now, if we just do the same calculation for our system, we have a 10 to the minus 6 level constraint. The pulsar's binding energy is 10% of its mass. So we divide by that, and we get a 10 to the minus 5 level constraint. So crudely, to first order, we improve by a factor of 10 on lunar laser ranging. That's kind of a big deal. But this is not really quite kosher, because the violation of the strong equivalence principle comes from the interior of the neutron star. If it's a scalar tensor theory, if it's accumulating extra scalar charge, it's because of the strong curvature inside the neutron star. And that is not a first post-Newtonian order region. You need a strong field theory to cope with the interior of a neutron star. And that's what matters to us. And specifically, it matters to us because funny stuff can happen in the strong field. For example, there's a slightly more advanced variant of the Brans-Dicke theory where there's a second parameter. The alpha naught says, sort of for ordinary weak field regime, how much does the scalar field matter? And so we can put an upper limit on alpha naught. But there's a second parameter, beta naught. And if beta naught is negative enough, then then the scalar field can be sourced in the scalar field itself. So if you've got something like a neutron star that produces lots of scalar density, that scalar density will then produce additional scalar density. You get this nonlinear growth. It's called spontaneous scalarization. And if it happens, pulsars will behave very strangely, no matter how weak the weak field behavior of the scalar is. So we need to consider a slightly more elaborate set of theories, but that's what's pictured here. And the left panel is comparing our result to other direct strong equivalence principle tests. And you can see that the dark gray region was ruled out by existing tests. We rule out the light gray region. And you can see that at the top of that panel is the 1713 result, which we improve on very dramatically. The two dashed lines are lunar laser ranging and a somewhat related test with a Mercury messenger satellite. And so we improve on all of those tests substantially. We can also, using this tool, compare our result to indirect strong equivalence principle tests, including dipole gravitational radiation tests. And you can see that we improve fairly substantially on those, including the Cassini light bending result, with the exception that if this funny stuff happens in the strong field, it happens first for O348, which has a 2 solar mass pulsar in it. That said, I think it's fair to say we provide a dramatic improvement on the best constraints on the strong equivalence principle that are available to date. And this is possible because we have this wonderful natural laboratory, a millisecond pulsar with 2 stellar companions. Thank you. Yeah, we've got a volunteer to run it, I think.
Somewhere there's a button. It looks like it's in the hands of somebody who knows what he's doing.
Fingers crossed. Yeah, so I encourage you to ask questions. It was a fun project.
Yeah, you have a very unique system, of course, with which you can do many things. And we talked about it briefly before when I first heard your talk. I'm not entirely convinced that testing EP is the best use of your system. So have you thought about any other tests you can pursue with the precision that it offers?
Yeah, there's a few avenues to follow, and one non-avenue to follow. So one is all that astrophysics that I kind of glossed over is actually interesting astrophysics, and I think questions about how did the system form are really interesting and are worth pursuing. And there are avenues to make progress on them. For example, the white dwarf can be observed optically, so there's work to be done there. The non-avenue is, there's a paper by Li-Jing Shao that argues that we could test Newton's third law here. In Newton's equations that I showed earlier, there are actually three masses. There's the inertial mass in F equals ma, and then in gmm over r squared, there are two masses. One is the body doing the attracting, and the other is the body being attracted. And he argued you could distinguish if the active and passive gravitational mass were different in this system. Unfortunately, I've done some simulations, and unless you're willing to assume that the inertial mass is equal to one of those two, all the differences get absorbed into a fit for the inertial versus gravitational mass, and you have no power left to distinguish active from passive gravitational mass. So unfortunately, that test does not seem to be possible. The system doesn't seem to provide the physics to distinguish active from passive gravitational mass. On the other hand, going forward, I think this system is it's a wonderfully stable timer. I think I would love to see it incorporated in the Pulsar Timing array, where they use arrays of precision timing millisecond pulsars to try and detect very long timescale gravitational waves passing over the Earth. So I think that would be an interesting step going forward. I'm not sure, I'm not really aware of any other kind of aspects of GR that could be directly tested with this system. The inner system is not very relativistic, so it's not losing much to gravitational waves. So you wouldn't get much of a constraint on dipole gravitational wave emission, for example.
Let us imagine a neutron stars binary and a white dwarfs binary, which belong to various stars clusters. And let us imagine they collide by forming four body system. Then the problem will persist because you had two white dwarfs and two neutron stars of different matter, of various matter. Let's wait or not.
So a quadruple system what we're able to do is compare the motion of the bodies in the inner binary, because they occupy nearly the same place. And so if the inner binary were two objects of the same kind, two neutron stars or two white dwarfs, we wouldn't have the contrast in gravity that we do here. So that would cost us. But on the other hand, if the outer companion were a neutron star instead of a white dwarf, that would help, not just because it gave more acceleration, but because in scalar tensor theories, this scalar field, as we saw in Brand-Sticky gravity, the scalar field would be produced, there'd be extra scalar coming from the outer companion, and so that would ramp up all the scalar effects of the inner binary. And so if we found a system like this, but with a pulsar as the outer companion, or a neutron star as the outer companion, even if we couldn't detect pulses, that would give us much more leverage on the equivalence principle. I don't know if that's getting towards what you were asking.
Okay, have we problems with systems of a neutron star, of one neutron stars and one white dwarf, or not?
So there are lots of such systems. The problem is that there's very little external acceleration to do this kind of test with. You can do other kinds of tests, for example, dipole gravitational radiation tests on those systems, and that's actually what the dashed dotted lines in the right-hand panel of this plot are. So those are very useful systems, and some of them are extremely relativistic and very interesting. But this particular test, you kind of need a third body to do a really good test of this kind.
Mm-hmm. Thank you.
Again, excuse me. What are the three masses, the value?
The pulsar is 1.44 solar masses. The inner white dwarf is 0.2 solar masses, and the outer white dwarf is 0.4 solar masses.
The outside one.
Yeah.
This is very interesting because it could be that, let's leave the one outside a moment, but 1.4 is quite high and 0.2 is quite small.
Yeah.
And if you have a binary neutron star in which you have mass transfer, what can happen is that the transfer from the one neutron star, the smallest, into the more massive one, create this famous condition that the smaller mass neutron star can pop out as a white dwarf, because it goes below the self-gravity. It's a limit which was introduced by Oppenheimer and Serber. This minimum mass of transition from a small mass neutron star to a white dwarf. That could help in understanding, because they are binary system with a very small mass white dwarf. But to me, the fascinating thing, which somewhat celebrate this lecture, if I may, is the fact that this gentleman is there. And this result tells a lot about the Kerr black hole, not as a black hole, no, forget about the black hole as such, but the mass formula of the black hole as a rest mass, as a rotational contribution, and as also the self-gravity in a neutron star.
Yeah.
Therefore, I have another time, and to tell you the truth, some moment I was even sleeping, but I was dreaming. It could be very well that it's a test for the mass formula of a Kerr black hole, in the sense that the Kerr black hole is not the Kerr black hole as a black hole, but a self-gravitating, rotating object with a self-interaction. You cannot distinguish. It goes as one object. And this is the big message of the Kerr black hole. Gravitationally, you can interchange, you can see the contribution, but the total mass is the one which counts. It's very, very, it could help in making an analogy to this.
It's an interesting analogy, but there's this funny phenomenon. Emmanuel Berthet and others put together a nice review of alternative theories of gravity, of which there are a shocking number. And the scalar tensor theories are very interesting for neutron star tests, because neutron stars accumulate loads of scalar charge, but black holes there's a no scalar Hare theorem, that in quite a broad range of theories, there's no scalar charge on black holes. Whereas quadratic gravity theories are not very interesting for pulsars, but are very interesting for testing, they produce different black hole behavior. And so, unfortunately, if you're considering alternative theories of gravity, you sort of expect neutron stars to deviate in a rather different way from black holes, if that makes sense.
But I am following general relativity.
Who knows where there's a small black hole?
Well, and neutron stars often come with nice clean clocks, and black holes usually don't.
Could I?
Thank you very much. Are there any more
I was just asking a question.
questions?
I think I have a very simple question. I presume that the white dwarf would be tidally locked to the inner white dwarf be tidally locked to the neutron star. Do you have experimental evidence that it is, or is that just an assumption? And would it make much difference if it wasn't?
Yeah, so it's not, a 1.6 day binary is actually not that tight a binary as neutron star white dwarf binaries go. And so it's not necessarily true that it would be tidally locked. Now, the white dwarf is about 25th magnitude, and so there are optical radial velocity curves. It's possible somebody with a really good eye could look at the spectrum and determine from the line profiles whether it was tidally locked or not. But fortunately for our result, we don't need it to be tidally locked. All we need is that it not be too flattened. And we worked out that as long as the rotational period was longer than, I forget, a minute, some number that was, as long as it wasn't spinning preposterously quickly, there wouldn't be enough tidal effects to pose a problem for us. So we, for this paper, kind of dodged the question, but it's an interesting question. It's one that there are the tools to hand to try and resolve.
Thanks.
Thank you, Professor Archibald, for your
On the